So welcome back again. So in the last lecture, we were discussing about the distribution of dopants in grown crystal. So we already have discussed about the segregation coefficient that we have defined. Okay, and then we have derived this particular equation for concentration of your dopants in the solid, and that is given by this particular equation. So we have already discussed this curve, okay, family of curve that we have got for different value of K naught, segregation coefficient, which is a material parameter. So this is the discussion that we have already did. Now, today we have to do a little more deeper discussion into it. So we'll look at that. So before that, I would like to mention here that in the previous lecture, in the equation number 4, there is one typographical error, so that you can correct. In there, I have written Ks instead of K naught. So I have defined our segregation coefficient as K naught. Okay. And in the equation number 4, I have written as Ks. So please correct those particular mistakes. So that is can be defined as the Ks. So now, first of all, again, just look at this discussion. So we left our discussion at this point. So what we have said, whenever our segregation coefficient K naught is less than unity, that time what happens is there is no uniform doping of the grown crystal. Okay, this is our ingot. So it is not having the uniform doping of your impurities. So what happens is progressively when we are pulling the crystal, okay, at the top, this doping concentration will be the minimum, and then it will be keep on increasing progressively as we are pulling the crystal. And at the bottom, you will find that the doping concentration of the impurity will be the maximum. Okay, whenever our K naught is less than 1. So this is what we have seen in the last lecture. So now we have to think of why this particular thing is happening. Okay, why this crystal is not having a uniform doping. So one thing that we could understand that K naught is less than 1. So what is the implication of having K naught which is less than 1? Okay, so that we have to look at today. Okay, when K naught is less than 1, then why this doping concentration is increasing in this particular grown crystal, that we have to look at. Okay, and how we can go on drawing the crystal which is having the uniform doping. Okay, how it can be controlled, because we know that this K naught, which is our segregation coefficient, which is a material parameter, is not in our hand. Okay, because it will be depending on the material. Okay, because it is the ratio of the concentration in your solid, okay, divided by the concentration of the dopant in the liquid at near the interface. Okay, so that way we have defined our K naught. Fine. So it is not in our hand, so that we have to look at today. So try to understand this. Okay, I will be explaining. Okay, so basically what we have said initially, what we have said is, let us say that if we had not started pulling any rod, okay, so we have already explained you. So our case number 1, you can revise. Okay, you can just recall your case number 1. In that, what we have said, we had said this, we have not started yet any means drawing the pulling any crystal. Then we had considered that the initial dopant concentration in the belt was C naught. Okay, this is our C naught. Okay, so we said it is initially C naught. Okay, then we had taken the case number 2 and we had started drawing the crystal. Okay, and in that case we had already drawn a certain certain mass, a certain weight of the crystal, and then there is a net reduction in the melt that we have observed. Okay, so then what we had said, because of the pulling, okay, when we are pulling this crystal, okay, and what we are considering is, we are considering that the K naught is less than 1. So what is the implication of this having K naught less than 1 is, when we initially had our dopant concentration in the melt equals to C naught, okay, and when we start slowly pulling this particular rod, okay, when we start pulling this particular rod slowly, then what happens is, because of k naught is less than 1, okay, let us say if this k naught is 0.7 for example. So what happens is, at the top of this, what we initially consider, this entire melt is having the same concentration, okay, when we had not started any pulling, okay. So when we had not started, that time we had this concentration of the dopant within the melt equals to C naught. But as soon as we start pulling this, okay, then what happens is, basically it is containing certain C naught concentration initially, but only 0.7 C naught is going into this particular crystal, okay, because this K naught is having value equals to 0.7, okay. So what we can see, only 0.7, okay, 70% of the concentration which is available in the melt is actually being transported to this particular crystal, okay. So what it reflects that, so only 70% is being transformed into the solid state, okay, it is going into the solid state, and the 30% is being rejected into the melt, okay. So not entire dopant is actually going into the crystal, only 70% is going into the crystal and 30% is being rejected. So what is the implication of that? If this will keep on happening, okay, we are keep on drawing this particular crystal, because we know that why it is happening. So because basically the solubility of any dopant, okay, in the melt and in the solid will be different, okay, it cannot be same, and that's why we have defined the segregation coefficient, okay. So because it is different in the solid and different in the melt, that's why it is not able to transport same concentration into the solid, okay. So what we are saying is 30% of this particular dopant is being rejected again. So when it is rejected, it will be available at the surface, okay. You can understand that where it is touching the surface, so slowly or progressively, what we can say, the upper layer of this melt, okay, upper layer of this melt will become progressively concentrated, means we can say it is progressively, the dopant concentration is increasing, okay. Progressively its dopant concentration at the top of the surface of the melt will start increasing. Initially it was having value equals to C naught, the entire melt was having C naught, but when we start drawing this pulling this particular crystal, then because of K naught, which is less than 1, some of the dopant concentration being rejected, and because it is rejected at the top of the layer, okay, top of the surface here, okay, therefore this particular top layer will become progressively, its concentration of the dopant will progressively increasing, okay. So this particular layer at the top will have more concentration than the layer at the bottom, okay. So at the top layer will have more concentration of the dopant, fine. Why? Because it is rejected by this particular crystal, and because it is K naught is less than 1, the same amount of dopant is not being transported to this particular crystal, that you need to understand, fine. So what we can have is, so what we are trying to explain, so if you remember the case number 2, what we said, that after drawing the pulling the crystal, we are having some melt is left inside this particular crucible, and that melt was having its weight equals to something around m naught, and then we said, okay, so it is m naught, and then it is having the total dopant concentration is equals to Cl. So what we had initially considered, that it is the Cl is throughout this particular crucible, but this is not the actual case, okay. So the case is that this top of the layer, okay, what we are saying is this top layer of this melt is actually having more concentration of the dopant than this bottom layers, okay, than this bottom layers. This bottom layers cannot have the same concentration, and this bottom layer is having its uniform doping concentration, okay. But within this particular layer, and now onwards I will calling it as a stagnant layer, okay, it is defined as the stagnant layer, okay, and within this stagnant layer, okay, we are having a variation of the concentration of the dopants, and obviously the concentration will be keep increasing, and at the top we are going to get the maximum concentration of the dopant. Why? Because this solid is actually rejecting the dopant, okay, rejecting the dopant into the melt. So because it is rejected at the top, okay, then it will slowly diffuse into this melt. Okay, so obviously the concentration at the top will be maximum. Okay, so you do not confused. This must be touching. Okay, I have not shown here in the picture like it is touching the surface, but it will be touching the surface. Okay, and therefore it will having the maximum concentration of the dopant at the top. And what we mean to say it is a stagnant layer. So when it is touching this particular surface, okay, our crystal is touching the this particular surface of the melt, okay, then there will be a particular depth, okay, of the melt, which is virtually it is immobile, okay, it does not make much motion. As I already explained that this crucible will be keep rotating, and this your pulling rod is also keep rotating in the opposite direction. Okay, so both are rotating. But when this crystal drawing is taking place, there is a very small upper layer which is virtually constant. It is not making any motion. The only motion is related to the flow of liquid, and that flow will be from liquid to solid conversion. Okay, that is the only flow that will take place, and there is no any other uh, flow or any motion of this liquid. That's why we are saying it is a very small thin layer, which is we are calling as the stagnant layer. And this stagnant layer will have different concentration of the dopant. Okay, and it is changing. It is having the maximum value at the top, and then it is keep changing. It is decreasing, and then it will reach to a particular value, and then this melt will have its uniform concentration of the dopant. Fine. So basically this layer we are considering, let us say this stagnant layer is having its width equals to delta. Okay, delta we are considering. Then what we are saying is at the top of this particular melt, okay, when we have started drawing the crystal, then this time the concentration of your dopant at the top of the layer, okay, at the top of the layer, we are calling it as Cl0. Okay, they are calling it as Cl0. So I will be taking direction like here I will take x equals to 0, and then x will be increasing downward direction. Okay, in this direction x will be increasing. I will be taking this top of the layer as x equals to 0. So I am calling it as Cl0. So it is the concentration of your dopant, okay, in the melt at the top of the layer. Then we can say what is the concentration of melt, concentration of the dopant in the rest of the melt. So that will be equals to your Cl. Okay, that will be equals to your Cl. And then this is the concentration of your melt, concentration of the dopant in the crystal. And again, I can define one of the variable, which is the concentration of the dopant inside the stagnant layer. I will be represented by C, or I can, or you can write it as Cx. Okay, so I am representing it by C. So this is the concentration of the dopant within the stagnant layer. So what we can understand, it is having maximum value, then it will be progressively decreasing, and then it will be reaching to the Cl. This way, our dopant concentration within the melt will change. So now we have to think of when this is the case, okay, because what we have said from this equation that or K naught is constant. Okay, so when K naught is constant, when it is always constant, and when this C naught is always constant, initial concentration, then why this CS is keep on increasing? Okay, that we have to look at why CS is increasing when we are keep drawing the crystal. Okay, this should not increase if C naught is initially constant and K naught is also constant. Should not increase. But the reason is when we are keep drawing this particular crystal, okay, what happens is this melt is progressively becoming becoming more concentrated solution. Okay, it means that the dopant concentration is keep on increasing and it is not constant at C naught. Okay, this is the fact. Okay, this is the fact. So basically what happens, this melt concentration is keep on increasing basically at the top of this layer, melt layer. Okay, So it is keep on increasing, and because this is increasing, and because K naught cannot change, K naught is still 70%. When this C naught will change, obviously the amount of dopant that will go into this particular crystal will also increase. So you need to appreciate this discussion because it is being rejected, and because this melt is having more concentration of the dopant, and therefore when we further draw this crystal, more number of dopants will enter, okay, into this crystal, and slowly this things will happen, okay, and therefore we cannot have the same profile, we can have the different profile, and slowly this your concentration of the dopant in this crystal will also increase. This is the reason, because our initial concentration is not kept constant. This is the basic reason behind it, okay, so that you try to understand. So now what we can do is, we just redefining the terms again, okay, we just redefining the terms again, because what we need, we want to grow a crystal which should have the uniform doping, okay, we have to get the uniform doping. So just we are trying to redefining the terms. So how we can redefine the terms? We have already defined the equilibrium segregation coefficient, and that was your K naught equals to Cs upon Cl. Okay. Initially, I have defined it as Cs upon Cl. Okay. And because we have not made any distinction between the means melt concentration. Okay. Melt means dopant concentration in the melt, because we considered the entire dopant is having the same concentration, okay, but right now we are saying that at the top of this, okay, top of this concentration in the melt will be Cl naught. So we have to specifically say this equilibrium segregation coefficient K naught was actually Cs upon Cl naught. Now I can define another segregation coefficient, which is our effective segregation coefficient. Okay, so I will define this particular term, effective segregation coefficient, as equals to Ke Cs upon Cl. So do not confuse. Last time I had defined this as Cs upon Cl, but that time we have considered that Cl is the concentration in the melt, and that Cl was throughout constant within the melt. Okay, it was not changing. But right now it is not the case. But even while defining the K naught, I said that this K naught is having Cs upon Cl, where Cl is the concentration in the melt at the top of the surface. Okay, so that's why we are just redefining it, and this way we can have this definition. Okay, so now let me derive the equation of your this particular segregation, this effective concentration Ke. Okay, we will be going to define the effective segregation coefficient Ke. Okay, and for that we need to follow a certain mathematics, certain physics. Okay, so we will be starting with the continuity equation. Okay, because here we have to write the continuity equation in this particular fluid, and then we can derive this particular equation for Ke. Okay, what will be the ratio of Ke if we are calculating Cs upon Cl in this particular case? So in the continuity equation, okay, so I'm just trying to explain you with this continuity equation. So if you go through in the semiconductor specimen, okay, if any semiconductor specimen, let us say we have the semiconductor specimen like this, if we have any particular block of semiconductor piece, okay, and let us say I am just considering a small volume, okay, so this is having length of dx, and let us say it is having a certain cross-sectional area is equals to A. So it will be having a certain volume which is equals to A into dx. So basically in this continuity equation, what we are interested in, what we want to find is, let us say we are interested in, we want to know that, so at particular time or at particular time duration, we want to know that if there is a net flow of current in one of the direction, let us say the current is flowing in this way or that way, okay, in whatever way the current is flowing. So let us say if it is flowing in this way, then what I want to know, is there any net increase of number of electrons or number of holes within this particular volume? Is there any net increase? Okay, that we want to calculate. So what we are interested in to know, whether there will be a net increase in the number of electrons, there is a net rate of change of number of electrons within this volume. So yes or no, that we have to look at. Okay, So basically, if we want to calculate how means there is a net increase of number of electrons or not, what we have to consider is we have to consider the different phenomena. Okay, so how to calculate this? First of all, if we are considering only one dimensional continuity equation, okay, so in the one dimensional continuity equation, what we have to say, the current is only flowing in one direction. Okay, only one direction. So there is no current flow from this direction like that, or the current is coming like this and going like that. Okay, it is only one directional flow of the current that is taking place in this particular block. So what we can say is, let us say if current is flowing. Okay, so what we have to do is we have to let us say this distance, if I call it as x, okay, as I have denoted here. Okay, so if we say it is x, fine, then if this is x, then we have to calculate the total current density which is entering to this particular small volume. Okay, so we have to calculate the total current density entering to this particular small volume. Then at this particular surface, we have to calculate what is the total current density which is going out of this volume. Okay, so let us say at x plus dx distance. Okay, so Jn x plus dx current density is actually flowing out of this volume. Okay, so first we are considering what is the inflow, what is the outflow. Okay, then we, as we know in the semiconductors, okay, in the semiconductor there are several processes. For example, there is a net thermal generation or photo generation of the current of current carriers. Okay, you must be aware of that. So there is a chances that within this particular volume, okay, so if we consider a very small volume like this, so if we consider this particular volume, okay, then within this volume we can have net generation of electron hole pairs. Okay, so it is having generation as well as the recombination of the charge carriers. Okay, so basically what we are saying, we are considering the total processes that may increase or decrease the number of electrons or number of holes within this volume, that we have to consider, because we are saying there is a net inflow. So due to inflow, there will be a net increase of the charge carriers within this volume. Similarly, when there is a net outflow, there will be a decrease in the number of charge carriers within the volume. Similarly, when we are having a net generation of the electron hole pair, then again it will increase the net number of electrons or hole pairs within this volume. And if there is a recombination, then there will be a net decrease in the electron hole pairs. So we have to consider all the phenomena, and then we have to talk about, is there any number of net increase of the number of electrons or holes within this volume, that we have to calculate. Okay, so very incremental volume that we are talking about. So to calculate that, we have to write a equation, and that equation is called as the continuity equation. Okay, so that you remember, we have to call it as a continuity equation. Okay, so in that continuity equation, what we have to calculate, see, we have to calculate the net increase of number of electrons. Let us say small n is denoting the number of electrons. Okay, so it is a rate of change of number of electrons within this volume ADX. Okay, within this volume ADX. So that we want to calculate. Within this volume, we want to calculate the number of rate of change of the number of electrons. Okay, so how we are calculating that? We are calculating the inflow of the current. Okay, GNX. Okay, so GNX is the net current inflow, and then GNX plus DX is the net current outflow. So you remember that it is the current density. So we have to accordingly get the current. Okay, and then we have to calculate the number of electrons. Fine. So that way it is actually represented. Okay, and you remember that when there is a net flow of electron, the current will be flowing in the opposite direction. So that we have taken into account because of this sign. Okay, so that you don't confuse, it is very easy to think of. Fine. So we have considered the currents which are having inflow, and then we are considering the current which are outflow. So we are considering the inflow as a positive sign. Here you can see a positive sign. Okay, and then we are considering the outflow as a negative sign. Okay, negative sign. Similarly, we have considered Gn, net thermal generation or photo generation of the charge carriers, as a positive side, and then we are considering the net recombination as the negative side. So let us say this is the net recombination rate, and then we have to multiply it through this particular volume. So this way we can have our continuity equation. Fine. So this is what we have written for our semiconductor piece. Okay, we have a semiconductor piece, and then what we can do is we can write this particular outflow of the current. Okay, we can write the outflow of the current as the Taylor series expansion. Okay, so here we are not dealing with this expansion of the Taylor series and deriving the equation. Okay, just we are trying to get the idea. Okay, just try to get the idea of the continuity equation, and we can directly use our results. Fine. So what we have to do, if you interested in, you can look into various books are there. Okay, and then you can find out how to do the Taylor series expansion for this particular current. And then we know that the electron currents or holes current in the semiconductor is the summation of the drift current plus diffusion current. So that equation we can replace, and then we can get the final equation for this particular continuity equation. Okay, the final equation of the continuity. Fine, including your thermal generation and recombination. So a similar discussion, okay, a similar analogy we can also give for this particular case. Okay, and modeling this one is a little tough when we are talking about the surface and the volumes. Okay, but still, because this stagnant layer will be very small. Okay, this thickness is very small. Okay, so what I will be considering is So what we can see is, we know that this particular liquid, okay, actually this liquid we can consider as, if it is going like this, it is entering to the stagnant layer and then it is going out of this stagnant layer. Fine. So what happens exactly is, we can consider there is a net inflow to this particular volume, okay, within this volume, and then there is a net outflow to this particular volume. So what we are interested here is, about the net increase in the concentration of our dopant. Okay, is there any net increase of the concentration within this particular volume? That we are interested in. Okay, a similar equation we can write, okay, as we have written for our this semiconductor piece. A similar equation we can write. So again we have to write the mass transfer equations. Okay, that equation we can write, and we can calculate, is there any net increase of the concentration of your dopant within this stagnant layer, because there will be a net inflow and then there will be a net outflow out of this particular volume, because some of this melt will be converted into the solid. Okay, so it will be a net outflow. So this way we can also write an equation. Fine. So that you have to keep in mind, and a similar equation we have to derive. So we are not deriving this equation, but we are just trying to see this result, the result of this equation, and an analogous equation we can write within the stagnant layer. Fine. So what we have done is, we have so after writing those equations, okay, for your GNX and doing the Taylor series expansion, okay, you will be getting certain equation like this. Okay, after doing the Taylor series expansion, you will be getting certain equation like this, where this is your net thermal generation and this is your net thermal recombination rate of your charge. So this type of equation you are going to get. So this portion you will be getting from the drift current. Okay, this portion. Okay, this portion you will be getting from the drift current, and this you will be getting from the diffusion current. Okay, so these are the different portions that you will get. Okay, so now what we can do is, we can write a similar equation. Okay, and in our case there is no net generation or net recombination of the charge carriers, or there is no generation of your dopant concentration within the stagnant layer. No generation, no such recombinations. Okay, this term will be neglected. So only term which are useful in our cases is this term, okay, and then this term. Okay, only this two term will be useful. So what we can do is, we can write a similar equation, okay, in the within the stagnant layer at the steady state, and we will be writing only these terms. Okay, B d square. Now this will be actually, here we have taken the dou by dou x. So because in the semiconductor, this number of charge carriers are actually depending on the lots of parameters. Okay, it is temperature dependent, it is time dependent, it is spatial dependence. Okay, but here it is only depending on this particular x. Okay, what we are writing is, we are writing it as a normal derivative. Fine. So here it is the diffusion constant of your electrons. We can write the diffusion constant of the dopant. Fine. And again, it will be a second order differential equation. So we are interested in the change in the concentration of your dopant within the stagnant layer. So we will be writing d square c upon dx square. And similarly, here we have dou np upon dou x. Okay. And you can see this is your drift velocity. Okay. Mu n into epsilon will be giving you the drift velocity. So similarly, we will be having another equation. Here again, we are having the velocity, but this velocity is your pulling rate. Okay, this velocity will be your pulling rate. And now we can write this as equals to dc upon dx. Okay, so at this side, we can write like dc upon dt. Okay, net increase in the dopant concentration. Okay, dc upon dt. So what we know that due to the conservation, okay, due to the conservation of the masses or due to the conservation of the dopants, okay, there will be no net increase or net decrease at the steady state. When we have already reached to a particular steady state, the number of or the rate of change of the dopant concentration will be zero. Okay, at the steady state when we have already reached to the steady state. Otherwise, it will be keep on increasing indefinitely. Okay, and it may be it may go to it may reach to the maximum value, or it may go to a max like infinity value. Okay, so when we have already achieved the steady state, in that case, this number of net increase in the concentration with respect to time will be zero. Okay, so this particular net increase will be zero. So now when we got this particular equation, which is a second order differential equation, we can solve this equation. Okay, we can solve this equation, and then we can get the solution like this. Okay, so getting this type of solution is very simple. Okay, c equals to a1 e to the power minus nu x upon d plus a2. This equation we are going to get. Now, after getting this equation, we need to find out the coefficients a1 and a2. Okay, these constants we need to find out. Okay, what should be this constants? Fine. So you can also represent c, either c or cx. You can write in the parentheses like cx. So this is the equation. Okay, that we will be going to get. So this is the concentration of your dopant within the stagnant layer. Okay, within the stagnant layer. So now we have to follow certain boundary conditions, and after applying the boundary conditions, we can get the values of a1 and a2. The first boundary condition that we can apply here is when our x is equals to 0, okay, means at the top of the layer. Okay, when we go top of the layer, then this c will be equals to cl0. We have already seen it. Okay, so we can put x equals to 0, then c will become cl0. So what equation we will get? The first boundary condition we can apply at x equals to 0. So we will be getting cl0 equals to, here it will become unity, so it will be becoming a1 plus a2. Fine. So this way we are going to get the first boundary condition. Now we can apply the second boundary condition. Okay, so what is our second boundary condition? You please try to look at this equation. Okay, I'll be explaining with this particular picture. Okay, so this second boundary condition says that it is the conservation of the total number of dopants at the interface. Okay, because you know that this we are saying this number of dopants should be conserved. Okay, it neither be created nor be lost. Okay, so it should have the conservation rule. Okay, so what we are saying at the top of the layer, okay, at the top of the layer at x equals to 0, when we talk about this particular surface, okay, then at the surface what we are having is some of the dopant material, okay, is being transported into the solid. Okay, when the crystal we are drawing, some of the dopant will be transported into the crystal. Okay, so it is going away from the surface. Okay, and at what rate it is actually being transported? It will be transported at the rate of pulling rate. Okay, so basically it is going away from the surface. Fine. Now this particular term we have written here as minus Cs into P. V is our nu is our pulling rate. Okay, so this is our nu, which is our pulling rate. So in the solid we are having concentration of our dopant in the solid is equals to Cs, and it is actually transported with this particular rate, this pulling rate. So because it is going away from the surface, we are writing minus Cs into nu. Okay, so this way this dopant is actually being transported out of this particular layer. Now if it is going away, then we have to see, is there anything which is coming to this particular layer? Okay, is there any dopant which are coming to this particular layer? Then the answer is yes. So that layer is coming from your the bottom melt. Okay, that bottom melt will be coming to this. Okay, so there is a confusion if you exactly see the picture, because when we grow the crystal is the growth of the crystal will be in the x direction. Okay, so exactly the melt never comes up. Okay, the melt position is actually going down, so that you remember. But while explaining, we can say that, okay, so this particular layer is actually having the same rate. Okay, it will go down with the same rate. Okay, it will go down with the same rate. This layer will go down with the same rate. Okay, because your crystal is growing. Fine, it will be growing and it will be coming down. So basically what we have to see, if we consider this surface as a constant, we can say that there will be a net inflow of the dopant. Okay, and because at the top of this surface we are considering the dopant concentration is Cl naught, we are saying that it is coming with the rate of Cl naught multiplied with the pulling rate, because again by which the material is being transported, by the same rate there should be a replacement of the melt. Okay, melt should be replaced. So therefore we are saying because it is having a plus sign, because it is coming towards the surface. Okay, it is coming towards the surface, and this was going away from the surface, so we have taken it to be a negative thing. Similarly, what we have said, because there is a dopant, okay, because of K naught which was less than 1, okay, some of the dopant concentration was actually being rejected. Okay, because it will be rejected by the solid, and therefore at the top of this there will be a net increase of your dopant concentration. And because of the dopant concentration which is higher at the layer, at the top of the layer, and it is lower at the bottom side, there will be a net diffusion of this particular dopant material in this direction. Okay, because you know that the diffusion will take place from higher concentration to the lower concentration. And as I already explained that the concentration of the dopant material will be maximum at this top layer, and then when we go down, the concentration will keep on decreasing. So there will be a net diffusion of this particular dopant concentration in this direction. Fine. So you know that the diffusion will be given by this particular equation, d into dc upon dx. Okay. So dc upon dx will be having a negative sign automatically. It will come negative sign. Okay. When we are calculating the dc upon dx. Okay. When you calculate the dc means final concentration minus initial concentration. The final concentration will be less than the initial concentration, and therefore this particular diffusion dc upon dx will come as negative sign. So it is going away from this particular surface. So this particular conservation rule we have to follow. And here we have neglected that there may be a certain diffusion, a very small diffusion may take place from your top surface to the solid also, but that diffusion constant is very small, and that's why we have neglected it. Okay, so basically we have taken these three components. Okay, so when we consider these three components, okay, we can write this equation. Okay, and when we write this equation, we have to solve it again, and then we have to proceed further. So what we have to do is we have to calculate dc upon dx at x equals to 0. So we have already defined in equation 10. Okay, we have already defined this equation for c. So we can calculate the dc upon dx. That will become out like this. Okay, you can do this, you can work out this, it is easy to get. Okay, so you will get this particular equation, then you can substitute x equals to 0 and then you can put into this equation. Okay, so if you do this analysis, you will be getting, here is the d, this is the negative sign here. Okay, then you can replace dc upon dx with this entire term. So if you substitute x equals to 0, this will become unity, you will be getting a1 nu upon d, so a1 nu upon d. Fine, and then this rest of the term will be as it is. So now you can solve this equation. Okay, so you will be getting a1 equals to cl0 minus cs, and then you can calculate a2 value equals to cs. It is very simple to do the calculation, you will get this equation. Fine, so now you can see what is the equation of the c after substituting a1 and a2. Okay, so we are going to get this c equation. Okay, this c equation will be equals to cl 0 minus cs e to the power mu x upon d plus cs. This is our equation for your concentration of your dopants within the stagnant layer. Okay, this is the equation for your uh, concentration of your dopant within the stagnant layer. Okay, so once we have arrived to this particular equation in this way, okay, we can go on plotting this. Okay, we can go on plotting this. So as we have already defined, when x equals to delta, delta is the thickness of your stagnant layer. So when x is equals to delta, then c will be equals to cl. Okay, we have said the rest of the melt is having concentration equals to cl. Okay, so that you remember. Okay, so you can see when x equals to x delta, this should be equals to cl. Okay, so if this is the equation, we can go on plotting this particular equation. Fine, so how to plot this equation, just to try to see this. Okay, so when we have x equals to 0, okay, this term will be becoming unity. So this is cl 0 minus cs, okay, and plus cs. So this cs and cs term will be cancelled out, so you will be getting c equals to cl 0, and then there will be a exponential decay. Okay, as x is progressing. Okay, there will be a net exponential decay. Okay, so there will be exponential decay, and x equals to lambda, it will be reaching to cl. Fine, so how this will be a plot, you just try to say this, at x equals to lambda, this c should be equals to cl. Okay, this is what our consideration. Okay, so when we have this liquid, okay, we have this liquid, then at c equals to x equals to 0, you can see x equals to 0. Okay, this c will be equals to cl0 at the top of the surface, top of the melt. Okay, we are having concentration equals to cl0, and then it is following this exponential decaying law, and then as we are substituting x equals to delta, this should be reaching to a cl value. This should be reaching to a cl value. Fine, so it is reaching to a cl value. This way it is reaching to a cl value, and then within this material, within this melt, okay, after cl, after delta distance, it will be remain constant. It doesn't change much. Fine. Now we have to look at that. When at x equals to lambda, we can go on further. Okay, and we can write these equations. Okay, at x equals to lambda, we can substitute c equals to cl. So there, what I have done is I have substituted c equals to cl on the left hand side, and then this term was on the right hand side, so I have transferred to the left hand side. So you will be getting cl minus cs equals to cl0 minus cs e to the power minus mu delta. Further, you can solve this equation. We have to get the equation for your effective segregation coefficient K. So in that term, we have to represent this equation. Okay, so if we keep on changing and we can keep on modifying these equations. Okay, just what I'm doing is just take this cl0 common out of this particular parenthesis. So what you will be getting is 1 minus cs upon cl naught. Okay, and then the cl naught I have divided over here. So you are getting cl naught over here, and 1 minus cs upon cl naught. We know that cs upon cl naught is defined as equilibrium segregation coefficient k naught. This term is representing your k naught. Fine. So we can further do the modification. Okay, we can further do the modification. So what we have done is we have added this term. Okay, you can just take this term out, CS upon CL naught. Okay, so if you take the individual ratios, CL upon CL naught minus CS upon CL naught. So this minus CS upon CL naught I have transferred to the right hand side. So I have written here as CL upon CL naught, CS upon CL naught, and then plus this term. Okay. Then what I have done with this CL upon CL naught, okay, I am multiplying and dividing CS upon CS. Okay, I am multiplying and dividing upon CS upon CS. This particular term I am dividing, multiplying. Okay, so if you do that, what we can do is we can have is we can write here is as CS upon CL. I can write this term at the bottom, that will be CS upon CL, and this I can write as CS upon CL naught. Fine. So basically what I can have is I can have CS upon CL naught. This can further be written as CS upon CL naught, CS upon CL. And this term is your K naught and this term is your KE. Okay, effective segregation coefficient. So if you remodify, you will get this particular equation. Okay. So this is one of the very basic equation, very important equation that we have arrived at. Okay. So what we have derived is we have derived the equation for your effective segregation coefficient, KE, which is equals to CS upon CL. Okay, this is your CS upon CL. So you can place it just to do the cross multiplication. You can it can go there and this can come to this particular denominator. Okay, so you will be getting this equation, and that equation will be equals to K naught. Here it is K naught. This is again K naught. And this is again K naught. So K naught plus 1 minus K naught and e to the power minus nu delta D upon D. Fine. So once we have arrived at this equation, we need to take care and we have to do a certain analysis. Okay. What analysis we have to do is, so what we are saying that the K naught is essentially a material parameter. Okay. And it is always be a less than 1. Okay. So when it is less than 1, okay, what we have said, when it is less than 1, we are saying that the uniform doping cannot be achieved. Okay, uniform doping cannot be achieved. Okay, so doping will keep on increasing from top to bottom. Okay, because there is a continuous rejection of the dopant material into the melt, and melt progressively becoming more concentrated solution. And therefore, when we keep on drawing this crystal, which is drawing at the bottom side, is having more concentration of the dopants, and therefore we are not able to get the uniform doping. But now if you want to get the uniform doping, okay, we have to just concentrate upon this particular equation, how to get the uniform doping. Okay, so now just to try to see, let us say K naught is still less than 1. Okay, but here you can see the the concentration of your dopant into the solid. Okay, concentration of the dopant into the solid is equals to Ke multiplied with the Cl. Ke, effective segregation coefficient. So if we are able to make, because Cl is the concentration of your dopant into the melt under your stagnant layer. Okay, and it is keep constant always. It will be constant. Okay, so when it is constant, if we are getting K equals to 1, then the concentration of your dopant within the material, within the solid, will be equal to means it will be a uniform value. It will not change. So now we have to when it will be a possibility, when we will get this possibility, when Ke is equals to 1. Okay, if Ke is equals to 1, if Ke is still less than 1, you can again assume that there will be a continuous rejection of the dopant, okay, into the melt, even if the Ke is less than 1. Okay, so how to make this effective segregation coefficient equals to unity? Okay, this is the question, how to make this K equals to unity. If you are able to make this K equals to unity, then you are able to get the uniform doping, even your K naught is less than 1. Try to understand this logic. How to obtain this? This is our question, how to obtain this. Even if we make the K equals to unity, we will be able to dope your crystal uniformly. Okay, so to get this k equals to 1, okay, just to look at this particular denominator term. Okay, so in the denominator term we are having one exponential factor e to the power nu lambda by t, where nu is the pulling rate and delta is your stagnant layer thickness, and d is the diffusion constant of your dopant into your material, like silicon. If you are having silicon, then the diffusion constant. So first of all, you try to see one thing. If I make this exponential term very small, or let us say ideally it is 0, let us say, if somehow if I am able to make it 0, then 0 is multiplied with 1 minus k naught. So this entire term will become 0. So once this entire term becomes 0, then this ratio will become k naught divided by k naught. Fine, and then the k will become equals to unit. Okay, and then we can achieve the uniform doping. Fine, we will be able to achieve the uniform doping. So basically, how to make this quantity very small or equals to 0, that we have to look at. So first of all, try to see this diffusion coefficient. Okay, so I have taken a certain values of the diffusion constant of your boron and phosphorus in silicon. Okay, so this is of the order of 10 to the power minus 10 centimeter square per second. Try to see this, 10 to the power minus 10. Okay, so when it is having 10 to the power minus 10 centimeter square per second, okay, so if you substitute this value over here, okay, you can also calculate the same quantity in the mm, okay, because our pulling rate is in mm. Okay, you can calculate this, you can do this exercise. Okay, just try to work out. Okay, so if you substitute this value, okay, so when you substitute this value, because d is in the denominator, okay, so this will become this power will become it is going to multiply with this. So what we can write, we can write minus nu multiplied with the delta multiplied with the 10 to the power 10. Okay, it will become 10 to the power 10 because it is having negative sign over here. Okay, negative sign over here. Okay, 10 to the power 10, exponential having a power of minus 10 to the power 10. You can understand 10 to the power 10 is a very large quantity. So exponential having a power negative, if the quantity is very large, then this exponential will become very small. So now you can see that, so it is 10 to the power 10 multiplied with the stagnant layer thickness and multiplied with the pulling rate. Fine. So basically when it is 10 to the power 10, and you know that the pulling rate is in the few mms per second. You know that the pulling rate. Okay. So when we have the pulling rate, we are having the stagnant layer. So what we have to do, if pulling rate, okay, if pulling rate is, if we make it a little higher, okay, it is in the 10 to the power, let us say it is in the few mm per second, okay. So you just try to work out this when it is 10 to the power 10 multiplied with few mm. So mm will be into like 10 to the power minus 3, okay. And then this delta will be in the order of 10 to the power like micrometers, okay. Micrometers or some mm. So it may be either 10 to the power minus 3 or 10 to the power minus 6. So 10 to the power minus 6 multiplied with the 10 to the power minus 3 and then 10 to the power 10. So it will be coming out as 10 to the power minus 1. Okay. You just take care about the mm in centimeter square. Okay. So that you take care of. So basically what I can say is to we have to, if we want to make this exponential factor small, okay, then ultimately we have to increase this numerator term. Okay, we have to increase this numerator term. So how it can be increased? By increasing the nu, which is your pulling rate. If we increase the pulling rate and if we increase the thickness of the delta. Okay, so this is the basic takeaway. Okay, so you have to understand, because we want to reduce this exponential term, then we have to increase this pulling rate and we have to increase the thickness of the stagnant layer. If these two factors will increase, automatically this exponential term will decrease. Okay, so how to get this k equals to 1? Okay, so first thing that we have understood is To get the uniform doping, how it can be achieved? By having a high pull rate. Okay, first of all, high pull rate, we have to have the high pull rate. Now to increase the thickness of the stagnant layer, okay, you remember that how the thickness of the stagnant layer will increase, because we know that there is a rotation of your crucible cup and there is a rotation of uh, your pulling shaft, so both are rotating in the opposite direction. Okay, and if we want to increase the stagnant layer thickness, okay, we want it to be a motionless melt. Okay, obviously the spinning rate should be slow. Okay, so try to think of it. If we have the spinning rate which is slow, if we have slow spinning rate, then obviously the stagnant layer thickness will be more. Fine, so that's why what we are writing is having a high pull rate and the slow rotation speed. Okay, if we do these things, okay, then we will be able to make this coefficient small, overall exponential coefficient is small, and therefore this term will vanish and this k will become equals to unity. Fine, and this way we can get the uniform doping. So I hope this must be clear. There is one more point is about, if we do not want to change the pulling rate or the stagnant layer thickness, okay, the another way of getting the uniform doping is to keep adding the ultra pure polysilicon into the melt. Okay, as I already explained you, what I have explained is we are not able to maintain the initial concentration of the melt, because this uh, melt concentration, whatever is at the top of the layer, okay, only 70% is going into the solid. So when it is going into the solid, then 30% being rejected again back to the melt. So the top of the melt is becoming progressively more richer into your dopant. Okay, so it will become dopant concentration is keep increasing at the top of the layer. So how this can be reduced? How it can be reduced? If we keep on adding the polysilicon into the crucible, keep on adding the pure uh, polysilicon crystal, then we will be able to maintain it at its initial value. Okay, so either this way or that way, you may be able to get the uniform doping. So try to uh, understand this particular concept. Okay, so I hope it must be clear. If you have having any query, you please uh, let me know your problems. Okay, we will be continuing from the next lecture. So thank you for today.